All right. Hey everybody, how you doing? It's Adam, PC Clear Computers and Games. We're going to continue Algebra 1. This lesson's going to be on algebra terminology. So we're going to learn some terminology about algebra. And this is very important before we start tossing X and Y's around and all that other algebraic garbage. So we're going to learn some terminology. Let's jump in and get started. First question I'm going to ask you guys is, what do we use numbers for? Right? Just think about it. I mean, we all know numbers. We all know how to add, subtract, multiply, divide, maybe with a calculator to help some of us. But we're going to wean ourselves off of that too, hopefully. But what do we use numbers for? Well, we use numbers to measure things, right? We know that there are 36 inches in a yard, 12 inches in a foot, so many feet in a mile. Was it 5,280 feet in a mile? We know that water boils at 212 degrees Fahrenheit or 100 degrees Celsius. Water freezes at 32 degrees Fahrenheit or 0 degrees Celsius. So we can measure things, right? We can measure the quantity of things. We can analyze things, right? We can say, well, this product here has to be kept at 50 degrees Fahrenheit or below, and we can analyze whether that has happened. We can analyze speed, right? Speed is nothing more than a rate of change. So we've gone 50 miles an hour for 3 hours. We've gone 150 miles. In algebra, we have calculus. That's really not the case, but we're not there yet. So, and we can also record things. Things like a checkbook, right? I can record my checks in a checkbook. I know I'm old school, and some people out there are probably like, what's a checkbook? But we can record things. We can record purchases. We can record maybe you have a food diary, you're trying to lose weight, so you're recording your caloric intake, right? Well, those are numbers. A calorie is nothing more than the amount of energy it takes to raise 1 gram of water 1 degree Celsius. It's a unit of measure. We can record things such as that. All right, so moving on. What kind of numbers are there, right? We know how to use numbers, or we know what numbers are used for, but has anybody thought what kind of numbers are actually out there? There are natural numbers. Oh, sorry. Let's go to previous. We're not ready for that yet. Okay. There are natural numbers, all right, which natural numbers go from 1 to infinity. When you see this little sideways 8 looking thing, just know that the number 8 didn't have too much to drink the night before. That's actually the infinity symbol, all right? And infinity means infinite, right? To infinity and beyond, as Buzz Lightyear would say. Well, infinity is just that. It's whatever number you can think of that's not infinity. You will never get to infinity. The infinity gauntlet, right, from Thanos. All right, it's infinite. Its power is infinite. Okay, so counting by ones. And yeah, I mean, you can count 1 rabbit, 2 rabbits. Kind of hard to count half a rabbit in nature. I mean, yeah, you can make half a rabbit, but it'd be kind of messy. But naturally, there is no such thing as half a rabbit. Okay? Whole numbers. Now, the only difference between whole numbers and natural numbers is whole numbers includes all the natural numbers, which means we're still going to infinity, but we start at 0. All right, we don't count at 1. You know, and 0 actually has a value, right? We don't say nothing plus 3 equals 3. That's not what we want to say. 0 has a value. It is 0. It represents 0 of something. Now, why did they come up with a whole new group of numbers just to add 0 instead of 1? Just to start at 0 instead of 1? Well, that's because in nature, or natural numbers, it's hard or impossible to represent 0 in that. I can't represent 0 gold bars in my room. I have no gold bars in my room, but it's kind of hard to, there's no such thing as 0 in nature, right? So naturally, there is no 0. The next type of numbers that we're going to talk about are integers. What the heck's an integer? Well, an integer is a fancy word for whole numbers, right? So we're going from natural numbers to whole numbers and into integers. And the only difference between integers and whole numbers is we go from negative infinity to infinity. Now, if you're not familiar with negative numbers, we're going to get there. We're just talking about terminology. So know when somebody says an integer, it means a whole number from negative infinity to infinity. That's all you got to know right now. Don't stress it. We'll get to the rest of it later. A rational number is a decimal number that ends or does not repeat. So a decimal number like 0.5, 0.125, those end and they do not repeat. So those are rational numbers. An irrational number is a decimal number that it never ends or repeats. For example, if you take 2 divided by 3 on your calculator or in Excel or something like that, you're going to get 0 dot and then a series of sixes. However many sixes you get depends on the memory limitations of your calculator or how many digits it can display. But you're going to get sixes to infinity, right? Which means it never ends and it never repeats because you're going to get nothing but sixes. Now, your calculator might round off the last 6 to a 7 or something like that, but we're not going to do that here. What you're going to see, instead of representing a whole bunch of sixes to indicate that something doesn't end, let me go to my here we go. Let me go to my ballpoint pen here. You're going to see 6 6, and then what they typically do is they put a line over one of the numbers to say, hey, this repeats for infinity. So we're not going to write a whole bunch of sixes. We're just going to write, well, 3 in this case. Another example of a decimal number that never ends or repeats is the Greek letter pi. Okay? The Greek letter pi is used in a number of different things. The first mathematical operations we're probably going to look at is the circumference or radius of a circle. Okay, excuse me, the circumference or area of a circle, because it has to do with the proportion between the circumference of a circle, which is the area around a circle, and its radius. Okay, or is it diameter? I forget which one it is right now. Just know that pi 3.14, and then it just goes on. It never repeats. There's no pattern of numbers. It doesn't go like 14789, 14789, 14789. It just randomly repeats itself. And people have tried forever to try to see if there is a pattern to the decimals, and there's just not. Okay. The next prime number that we're going to talk about, let me get back to my point here. The next type of number that we're going to talk about is a prime number. Okay, a prime number is simply a number that is divisible by 1 and itself. All right, and it has to be greater than 1 as well. We're not talking about greater than, less than symbols yet. That's later on in this presentation. But it's divisible by 1 in itself. It can't be 1. So the first couple of prime numbers are 3, 5, 7, 11, 13, 17, 19, 23, 29, and 31 are the first couple of prime numbers. The number 2 is kind of weird because it's considered prime by some people and non-prime by others. And it's because when you get to higher level mathematical proofs, if you put the number 2 as prime, it kind of breaks a few things. So this is going to be a matter of convenience in this class. If we want 2 to be prime, it'll be prime. If we don't want 2 to be prime, it won't be prime. So at our level, we don't care if he's in or out, basically, is what I'm saying. All right, let's look at some algebra vocabulary. We have an expression. All right, an expression is just a combination of values. 2x squared plus 4x. All right, don't worry about that little 2 that's floating away. We're going to get to what that is in a minute. Just know that an expression is a combination of values. And this could be a minus sign. It could be a division sign. It could be something like that. It really doesn't really have to be a plus sign. we're going to look at a term. A term is a grouping together of one or more variables or numbers. 3xy plus 5x minus 6 has 3 terms in it. Boom, boom, boom. Okay? Anything that's separated by a plus sign, a minus sign, divide sign is considered a term. Multiplication is kind of strange in algebra if you're just coming into algebra for the first time. And the multiplication symbol is implied between the 3, the x, and the x and the y, and the 5 and the x here. The multiplication symbol is implied because it just really doesn't need to be there. Equation shows that things are equal to each other. So if I say 3x squared plus 4x equals 7, that means that this quantity here is equal to 7. It shows equality. And I don't know if you guys ever realized that when you were doing basic math in school, or maybe you took algebra and didn't do so good in it. And I really think that's a fundamental concept here, and it gets glossed over in a lot of math classes, is that the equal sign shows equality. Both these are equal to each other. All right, and then there's some funny things you got to do with equal signs and stuff like that, and we'll get to that later on. But just know that an equation shows that things are equal to each other. So I have two terms here, one term on the other side of the equation. So these two terms, when added together, equal 7. Okay, an operation, a resulting number of two or more numbers. So if I have x plus y, x minus y, x times y, we use the asterisk a lot to designate multiplication in algebra. We don't use x like you were taught in elementary school because x is a variable in algebra. So you don't want a whole bunch of x's running around when you mean multiplication, or a bunch of x's running around when you mean a variable. It just gets real confusing real fast. Then we have the division, or the forward slash. We're going to use that for division in this course. We're not going to use the let me see here, the thing you probably used in elementary school, which was the line with the dot here and the dot here. Right? We're not going to use that so much. We're evolving. We're going to use the forward slash to denote division. This little guy right here, he's actually supposed to have a line like that, maybe a straight line like that. But this is called a radical symbol, and we use this for square roots and such as that. If you don't know what a square root is, don't worry about it. We're going to get to it. Right now, you just need to focus on what an operation is. Now, I mentioned the word variable, and that's what we're going to define next. A variable represents an unknown value. X plus y equals z. Well, that's 3 variables. X is a variable, y is a variable, z is a variable. So if I say 3 plus 3 equals 6, I'm replacing those variables with known values. 4 plus 4 equals 8. It could be 6 plus 6 equals 12. I don't know, because the value of these variables can, well, vary. All right, a constant represents a known quantity. And I just kind of threw down the number 54 here. Let me get back to my pointer here. There we go. I just kind of threw down the number 54 here because it's a constant number. It's always going to be 54. It's never going to be less than 54. It's never going to be more than 54. It's just going to be 54. It's not even going to be 54.00001. It's going to always be 54. It's a constant. All right, now, I told you earlier on, don't worry about that little number that's floating away here, right? That's because that little number is called an exponent. An exponent's a small superscript. That's what happens when it's above it. When it's floating away, it's superscript. When it's sinking, it's subscript. Okay, remember, Superman flying away, superscript. Submariner swimming in the ocean, he's sinking, right? Well, he doesn't sink, he just swims. But anyway, small superscript number used to show repeated multiplication. So, for example, and this is where we're going to throw in some other terminology that we just learned about a couple slides back, x to the 4th power is equal to, remember what the equal sign means, equivalent to x to the fourth power, x with a subscript of 4, which is also equivalent or equal to x times x times x times x. All right, so used to show repeated multiplication. So if x, let me go back to my pointer here, if x equals 2, well, then that's 2 times 2 times 2 times 2, right? So that would be 2 times 2 is 4, times 2 is 8, times 2 is 16. So x to the fourth power is equal to x times x times x times x. X equals 2, which equals 2 to the fourth power, which equals 2 times 2 times 2 times 2, which equals 16. 2 times 2 is 4, times 2 is 8, times 2 is 16. Don't add the 2's, multiply them. Okay? Let me go back to my pointer. Algebra operations, and we've kind of gone over this a little bit here already. We all know addition and subtraction. Multiplication, we're going to use the asterisk or the dot. I like using the asterisk when I'm making slides because then you know it's an asterisk. This might get misconstrued as a decimal point, and I don't want to confuse anybody. Division, we're going to use the slash. We're not going to use this symbol so much. I just put it in there for a relative reference. We're not going to use that so much. That's a little too elementary, I think. So we're going to evolve and we're going to use the forward slash. This is called a forward slash because it is falling forward. There is another symbol called a backslash. It's called a backslash because it is falling backwards. But this is a forward slash. Square root, let me add that little gimmick on there for you. Again, that line is supposed to be straight. Just pretend it's a straight line. I'm not an artist. All right, so square root. This is a radical sign. Absolute value is just two straight lines here. All right, and basically an absolute value, just to give you a brief notion of it, whatever you take the absolute value of is always positive. So I could have the absolute value of 1,000,000 equals 1,000,000. The absolute value of negative 1,000,000 equals 1,000,000 because the absolute value only returns a positive value. And then finally we have pi or pi with this little symbol right here is what we represent pi with. It's the Greek letter pi. Again, it's used a lot in circle and cylindrical shapes and stuff like that to configure, to compute circumference, area, volume. Now, you see a lot of these things in Algebra 2, the parentheses, the square bracket, the curly bracket, right? And these symbols are used to designate grouping, all right? And the reason we use them to designate grouping is because we have to deal with what's in the grouping symbols first. For example, if I take parentheses, open parentheses, 5 plus 10, close parentheses, divided by 5, I have to do what's in the parentheses first. So 5 plus 10 is equal to, well, 15, and I keep the parentheses there just as a relative identifier. You want to make sure you define your parentheses really well so you don't mistake it for a 1 if you're writing these things by hand. Again, clearly write things out. Your handwriting will screw you every time in this if you let it. So 15 divided by 5 is equal to 3. Okay, that's cool. Now, if I didn't have the parentheses there, then the order of operations would take place in which I would do multiplication first in this problem. 10 divided by 5 is 2. 5 plus 2 is equal to 7, which I get a totally different answer. So yes, parentheses do make a difference in the order of operations. If you're not familiar with the order of operations, again, we're going to get there. Don't worry about it. Algebra relationships. We already went over what an equal sign is. I'm saying this is equal to that. Not equal to. Now you see this represented a couple different ways. Not equal to is the 2 is a less than symbol and greater than symbol put together. or it's an equal sign with a slash through it. Approximately the same, which you get these two little wavy lines here. Okay, and we can say, let me get to my pen again here. I can say, oh crap, let me see, pointer options, ballpoint pen, yeah, okay, 4.01 is approximately equal to 4. All right, less than or equal to is this little bracket here, open to the right with a line under it. All right, if it doesn't have the line under it and you just have the open bracket pointed towards the right, it is just a less than symbol. 3 is less than 5. 3 is less than or equal to 5. 3 is equal or, excuse me, 3 is less than or equal to 3. All right, now if we have less than and equal, well, we got to have greater than, right? So we have greater than or equal to is the same thing. It's just the angle bracket, the arrowhead, whatever you want to call it there, is pointed to the left. So greater than or equal to, that thing's pointed to the left with a line under it. Greater than is the greater than symbol, angle bracket, arrowhead, whatever you want to call it. I'm going to call it the greater than symbol because that's what it is. The greater than symbol is open to the left. So 10 is greater than 4. That's a true statement. 10 is greater than or equal to 4. That's a true statement. Because when you say greater than or equal to, only one of these has to be true in order for the statement to be true. All right, let me get back to my pointer. There we go. All right, so algebraic relationships. How does one set of numbers relate to another? Very important concepts here. Come back, look at this slide again and again and again. Make sure you have this down, okay? Because it's really kind of integral stuff that you got to get, that you have to understand. All right, now here's a tricky thing about algebra that they don't tell you. They just expect you to know or expect you to figure out for yourself, and I think it's the most unfair thing in the world. So what we're going to do is we're going to talk about what type of answers we get in algebra. And I think up until algebra, everybody gets a final answer in math. And what I mean by that is everybody starts out with 2 plus 2 equals 4. Well, that's a final answer. 3 plus 3 equals 6. 100 divided by 10 is 10. You're getting actual answers with math. And then they just throw a curveball at you in algebra. Because sometimes in algebra, you don't get an answer like that. You don't get a clear-cut answer like that. It depends on what the problem is asking you to do. For example, if it asks you to simplify a problem, all it's doing is asking you to reduce the number of terms using algebraic methods and tools. And we're going to get into what those methods and tools are later on in this course. Factor. Well, factor just means change 2 or more terms, okay, greater than or equal to. See, we're using this stuff from the last slide already in this slide. Okay, change 2 or more terms into one term. Easy enough to do. And then finally we have solve. Get the final answer for a variable, usually x. If I say 3 plus x equals 6, well, you can probably figure out just through simple deduction that x is equal to 3, because 3 plus 3 is equal to 6. All right, that's all we have for this installment of Algebra 1. Let me know what you think, all right? I'm going to get more consistent with putting out videos because I think people like the videos. I think it's helping them. But you let me know. Thank you for watching.